Hey everyone, this is Darshan Santan and welcome back to another video on differential calculus here. So in this video, we're going to be talking about linear approximations. So now what are linear approximations? Well, they are ways to approximate the value of a function at a point. So in most cases, you may be like, why do we even need this? Even without a calculator, you can evaluate a good amount of functions at any point. And this is true for things like linear functions and quadratic functions. But what happens when you get to more complex functions, such as, say, like the square root of x, or like a cube root of x, or maybe even something like a natural log of x? When you get to functions like these, the value of a function at a point is not something that you can easily analytically calculate, right? So therefore, if you don't know the value right off the top of your head and you don't have a calculator, it's really difficult to see what it might be. So therefore, we're going to use some kind of an approximation to sort of get a good idea of what that is. And that's what linear approximations help us do. So just to give you a little picture of what we're trying to solve here, let's consider the function y equals x squared, right? And or the y equals square root of x, my bad. So, and let's say we want to figure out what f of 1.2 is, okay? So let's just plot that over there. And so if we want to figure out what that is, well, obviously we don't know that off the top of our head, right? So we're going to need to use some kind of linear approximation to sort of get a good idea of what that might be. Okay, so here's how we do that. So there's two methods of linear approximations that you can use that we're going to cover. And the first one, which I kind of like more, is the way of using the tangent line. This is a pretty straightforward way to understand, and it's also pretty useful for most points, right? So here's what you do. So you find the tangent line equation, right, to a known point close by to the value you want to solve, okay? So, and then you use the function of the line to estimate the value of the function. All right, so you'd use this function to sort of spit out a value that you could use as a reasonable estimate for what the value of your function would be at the point. Okay, so this is what we would really do. But now let me give you a little bit of a better picture of why this works and what it might look like. So here's our graph again, and let's say we want to find what f of 1.2 is. Now let's sketch the tangent line at a point close to 1.2. Let's try x equals 1. So that's what the tangent line would look like, okay? So that's x equals 1, and that is x equals 1.2. Now, if we zoom in close, you can see that the tangent line goes awfully close to f of 1.2, right? The tangent line is going really, really close over there. So therefore, what we're going to do is that's why we can use this tangent line as an approximation of the function of f of 1.2. And also keep in mind, this is only true for points close to x equals 1, right? If we wanted to get a point, say, like x equals 3.7, then we need to use a tangent line to a different point in the graph. Okay, so here's the idea that we're going to use here. So the idea is this. So let's say for the tangent line through point, let's call that C, right? In this case, C would be 1, but just to be general, let's call it C. Tangent line through a point is very close to the value of f of x for all x that are close to C, right? So for any x values that are close to the value of C we have chosen, the tangent line represents good representation of what the function might look like there. Now, if you chose a point x equals 10, well, then the tangent line that goes through this point is not a very good representation, right? Because tangent line's way up here and that point's way up there, is way out here. So therefore, for points close to C, however, the tangent line's a good approximation. It's close enough, right? So therefore, that leads us to the point 2, which is that the function of the tangent line can be used to estimate f of x. Again, and this is only true for points close to C, right? So this is basically the idea that we're going to use. Because the tangent line goes so close here, we can use the function that the tangent line has, use that function, a relatively simpler linear function, to calculate the value of our given x value at that point, and that should be a pretty good estimation. So we get the function of the tangent line, plug in the x value we want. It's going to spit out some output, and that output is going to be a pretty good estimate of what f of 1.2 is, or what your f of x is actually going to be. Okay, so that's the idea we're going to use here. Now here's the actual problem solving plan of action. So the theory is all good and stuff, but here's a little bit of advice on how to solve the problems. All right, so when picking a point C, okay, make sure of the following. Make sure you know f of C, and also make sure it is as close to x as possible. You want to get a known value as close to your given value as you possibly can, right? So once you have all these, use slope intercept to write your tangent line equation. So you'd use your derivative to calculate a slope, and then you'd use the point to calculate the intercept, right? So you'd use that to calculate the other parts of the line equation, right? So that's what you do, and then plug in x, and then you have your answer, right? So this is basically what you would do. Now let's actually try to solve the problem we had in the previous slide. Let's approximate the square root of 2. Okay, so the first thing we need to do is we need to find a slope, right? So let's go ahead and calculate that. So so if f of x equals square root of x, that's the same thing as x to the 1/2, right? So if we took a square root of, if we took a derivative of that, we're going to find that f prime of x by basic power rule is going to be 1/2 x to the negative 1/2, right? And now we have our slope. We have a function that tells us our slope. And now, but before we actually find the slope, we need to pick our c, right? And because we know a point close to 1.2, we're going to pick c equals 1. Okay, so now f prime of c is going to equal 1/2 1 to the negative 1/2, which is basically like 1 over 2 square root of 1, which is going to be 1/2. Okay, so that's what that is. And now secondly, let's go ahead and find f of c, and this is basically going to be square root of 1, which is 1. All right, so now we have all the ingredients we need to set up our tangent line equation. So let's go ahead and do that now. Okay, so what we would have now is we're going to have something of the form y equals m x minus x1 plus y1. All right, so plugging in everything we know, this would be y equals 1/2, right, x minus x1 is just going to be 1, right, because that's the c we chose, yeah, plus y1, which is just going to be f of c, and that's also going to be 1. So that right there is the equation for our tangent line. And now last but not least, we just have to plug in that x, right? So now you just plug that in, and we're gonna have y equals 1/2 1.2 minus 1 plus 1, and 1.2 minus 1 is just 0.2, so this would be 0.5 0.2 plus 1, 0.5 of 0. Half of 0.2 is just 0.1. So 0.1 plus 1 is just going to give us 1.1. Okay. So that's basically that's our approximated value for the square root of 1.2. Now, if we actually plug this into a calculator, we find that the actual value, right? The actual value is 1.09545-ish. So 1.1 is a pretty darn good estimate of what that is. So these are really, really close. Right? So as you can see, this is a really good way of estimating the value of a function at a point. If you found this video helpful, please do like, share, subscribe, leave a comment, and check out some other videos. See you next time!